Maybe we can talk a little bit more about about the science and the very idea meaning with respect to technology enhanced learning goals. The way I like to do that is really think about how statistical modeling relates to science, because obviously a lot of doing science involves working with quantitative results. But what is the act really of statistical modeling? How does it really relate? Well, first thing is statistical modeling itself is not science. Science is disproving a theory. So you have to start with an idea, and statistical modeling fits into that, which is really the next point. You don't really commonly do model fitting to produce hypotheses. You build models and gather data to test hypotheses. One of the simplest or most common cliches about this is that correlation is not causation, but correlation may help suggest mechanism. So our recommenders are, in the simplest form, sometimes based just on correlations, but we really can't impute much more than that. By studying enough correlations, we may have some ideas, but even then we're not really doing science just by studying those. So in effect, simple applications of social recommender technology, as they commonly are done now, really just use data to suggest basic statistical hypotheses. Recommended items apparently would fit some underlying model for a phenomena. They, in some sense, probabilistically disprove hypotheses. If items are not recommendable, that must rule out some models that might explain the phenomena. And they can help us, if we study the data a bit, discover relationships which may at least imply some mechanism, or put another way, tell us about required properties of some model fitting a hypothesis. When you look at it that way, it really is the case that interesting technology-enhanced learning problems require social recommender technology that delves deeper into meaning than some of the most common applications out there right now. And I want to give you 3 examples what we mean by that might help you fix these ideas a little bit better. The first is the Netflix challenge example, which I think most people are probably familiar with at this point. I attended the 2007 International Conference on Machine Learning and noticed something interesting. There were a number of papers there where the work on machine learning techniques was sort of quietly at some point in the talk explained that this work was being developed because they were working on the Netflix challenge. There was one paper there, though, that I actually quite enjoyed because the authors were quite unabashed that they wanted to win the $1 million, and they thought the best way was just to do statistical model fitting until they found the model that fit the data best, and that should give them the best chance at winning the million. And in fact, at that time, they claimed to have achieved the best results to date by that sort of approach, which I think leads us to a couple of related questions of whether the superficial semantics they were after really are the basis for good recommendations, or if they're not. Maybe they are just good for winning the $1 million, but not good for making recommendations. The first thing is we really need to think about what recommendation applications are 5-star ratings even useful data. I don't think that really is well understood to now, and I think there could be, if you have rating data available, it could be very interesting problems to try and show why or why not that actually is good for a recommendation application. Is the particular data set you have, whether it's 5-star ratings or anything else, really representative for the recommendation problem you want to do? I mean, these Netflix movie ratings may be a very small subset of the population who happens to just to like to do ratings. As I mentioned in an earlier slide, that may just tell you more about rating behavior and not about anything on which movies can be used to make recommendations to a general population. What is the knowledge in the ratings about? What is the real hypothesis and the model being used to prove or disprove the hypothesis? You could probably think of a number, but I don't think there's anything that's immediately implied by just the fact you have these 5-star ratings. Then just kind of this summary question that sort of recaps all of these and expands a little bit. Is the knowledge and model that is essentially implied by that data, or that can be that data can be used to speak to actually the basis for useful recommendations. I think what we see here is that simply fitting compiled stats, as useful as it may be for some purposes, may not be sufficient for many technology-enhanced learning applications. And I'm sure you all have examples that is probably almost trivial to you as a point, but I think to the social recommender technology community that is not as trivial as it might seem. Another example, which is sort of in the lore but is true, is I'll call the market basket example. And this is not the story many of you may have heard about somebody studying list of items, cash register tapes, and discovering that a lot of tapes had diapers and beer appearing on them, so that you ought to put diapers and beer together on a shelf to increase sales of both. This is actually a different story about how, at least for several years, their simplistic semantics for association lists, and we can call those market baskets or cash register tapes, can be misleading in terms of what they really say for even simple recommendation technology. What the scenario was that they mined large numbers of association lists, which in this case were purchases, for statistically significant pairings. And it wasn't just one researcher or economist that did this. This was repeated many times. The problem was that when that information was used to suggest marketing scenarios, and the scenario that's typically used to suggest was these two items occur together. If I put one on sale and people get that, maybe they're likely to buy the associated items because we've made sort of a recommendation there. That isn't necessarily a direct analogy to how all recommenders work, but one can also think, when I give you the rest of this, of other situations or other recommender applications in which similar, this is the problem I'm going to describe, similarly could arise. Well, the problem that they observed was there's a highly variable acceptance rate for recommended items, no matter how you define them, given items already in the basket using these pairings. And it took a little while, but I think in sum, one can describe what they found out is that the simple semantics, if you like, you may also like, they are true enough, but in fact, the kinds of items that we typically will find in a retail situation fall into at least two categories. There are complementary goods, which are defined to be those goods that if you have one, you are likely to want the other. You can think of razors and blades maybe. And there are substitute goods. If you have one, you likely don't want or need the other, at least at any particular point in time. So you could think of hamburgers and hot dogs go together on a picnic, but if you've had a hot dog, you probably don't want a hamburger. So for a large enough set of associations, pairs of substitute goods will show up enough to be detected, just because of, you can imagine, people shop for picnics and people then shop for at home. And if you're shopping for picnics, you might want to get what everybody wants, so you get hamburgers and hot dogs. But if you're shopping at home, for this week you want hot dogs, next week you want hamburgers. So in many specific instances, you only want one or the other. And one can think in media items that you may not want 10 songs that are exactly the same. You might actually want diversity or something like that. So here's a case where simple semantics, in some sense, are statistically true enough, but they may be misleading or irrelevant for many apps, including technology-enhanced learning applications. And I think the problem of determining or detecting complementary and substitute goods, or items in any recommendation situation that have these two characteristics, actually is a very interesting research problem that some of you working in technology-enhanced learning, I think, may come to some interesting discoveries if you haven't already. Again, we look forward to hearing from you if that concept fits into any work you've done and any results you can point us to, because we believe it's a very important concept.